How hot does it have to get before human beings simply can't cope with the heat and die? Well, it depends. How much extra energy is needed to raise the Earth's temperature by a set amount? Well, it depends. These things depend on a specific climate variable that is hard to measure, nobody's much talking about, that makes producing those climate computer models much more difficult, and yet can make a huge difference to the impact of climate change on relatively short timescales. That climate variable is water vapour, and it's creating a surprising paradox that we're only just finding out about. Let's take a look. The easy bit here is to understand that water vapour is fundamental to life on Earth. You don't need to be a scientist to get that it's the basis for clouds and therefore for rain, which means that it sustains plants and forests and provides us with drinking water. All of that we know, but it goes further than that. On the extremes, it can be the difference between literally life and death. Lack of moisture in the air can be a factor in the incidence of wildfires. A high degree of moisture combined with high temperatures can make heat stress worse for people to the point where thousands will die. If you've ever wondered why scientists find it so difficult to model the world's climate, one of the reasons is around the difficulties around water vapour. There are 4 ways that water vapour affects the Earth's energy balance. Firstly, water vapour contains what's called latent heat. When water vapour condenses into liquid water, it's a heat generating process. In the same way that when liquid water evaporates, it's a cooling process, which is why sweating cools you down. We'll come back to the whole sweating thing in a few minutes. The moving around of water vapour creates what's called the hydrological cycle. 70% of the surface of a planet is water, and the movement of moisture from evaporation to condensation to precipitation leads to all of the dynamic climatic events that we see and have seen throughout history. Latent heat gets released in the tropics, radiative cooling takes place at the poles. The difference between the two temperatures makes a whole lot of dynamic action, including various regional effects, such as the El Niño Southern Oscillation, the incidences of drought and flooding events, and all of the rest of it. Secondly, it's a greenhouse gas, absorbing certain wavelengths of outgoing long-wave radiation. It's the largest and most significant of the greenhouse gases, although it's only in the atmosphere for a relatively short period of time, unlike the long timescales for CO2, so it's a feedback mechanism rather than a prime mover. Initial warming created by CO2 and other gases means you then get more water vapour, which creates even more warming. Thirdly, water vapour produces clouds, which have a significant but highly variable impact on temperatures, partly because the white clouds have what's called an albedo effect, reflecting incoming sunlight and thereby cooling the planet, but also because they reflect outgoing radiation back down, which has a warming effect, which is why clear nights are generally the coldest. And then fourthly, because the amount of moisture in the air affects the amount of energy that it takes to raise the temperature of that air. That's important for those climate models because you have to factor into the model how much additional energy will lead to how much additional warming. In the past, climate models have assumed constant relative humidity over time, which means that more energy would be needed to raise global temperatures than would be the case if the air was dry. Now, that may well be a reasonable assumption, but it's hard to prove in practice. Historically, we've measured humidity a lot less well than we've measured temperatures. Part of the challenge is that humidity is not just one thing, and people find the differences confusing. One of the key questions is how saturated the air is. In the case of the beaker on the left, you have evaporation taking place, and the air above the water is relatively unsaturated. So the fast-moving water molecules break away from the liquid surface and enter the air as vapour. While some of the water molecules are leaving the liquid, evaporating, others are returning, condensing. In relatively unsaturated air, the number evaporating is going to be a lot higher. But in the second beaker, where the air above it is saturated, the number of molecules evaporating is matched by the number condensing, and no liquid is lost. So the degree of saturation makes a difference to whether evaporation can take place or not. So, what are the different ways that you would measure humidity? Here's where it gets a little bit complicated, because there's a number of different ways. None of them are particularly intuitive or easy. Imagine it like this. If you had an isolated parcel of air, which has a certain amount of water vapour in it. Now, you could compare the mass of the water vapour with the volume of the air to get the water vapour density, or absolute humidity. But of course, the higher in the atmosphere you go, the less dense the air becomes. So you might also compare the mass of the water vapour with the total mass of all the air in the parcel, which would give you the specific humidity. Or you can compare the mass of the vapour with the mass of the dry air to give you the mixing ratio. Or you might measure the overall vapour pressure. Air pressure at sea level is a combination of the nitrogen and the oxygen and the water vapour. So, given that the quantities of the first two are known, measuring the overall vapour pressure can give you the air's total water content. Or, the term you've most likely to have heard is that of relative humidity. Now, this doesn't tell us how much water vapour's in the air. It tells us how close the air is to being saturated. And that matters because the amount of water vapour it takes to saturate the air is different depending on the temperature. The relative humidity then is a percentage figure, calculated from the water vapour content divided by the water vapour capacity at that temperature. So look, first thing in the morning, the lower temperature means that the air becomes saturated with a lower amount of water vapour, which is why you get dew first thing in the morning. In the heat of the afternoon, on the other hand, the same amount of water vapour would be nowhere near saturation point, which is why that when you sweat in the heat, that sweat will evaporate and cool you down. And therein lies one of the challenges, because if you get high temperatures and high humidity, that's where you can get heat stress leading to actual loss of life. A normal human body has an internal temperature of around 36.8 degrees Celsius. To maintain that requires skin temperatures of around 35 degrees C to keep the body successfully directing the heat outwards from the core. Once the air is above that temperature, the body can only shed that heat by sweat-based latent cooling. Remember, latent heat comes from evaporation or condensation. Evaporation is a cooling process, hence the sweating. Condensation is a warming process. So if you get a saturated heat above 35 degrees C, what's called the wet bulb temperature, then sweat-based cooling simply stops working. And that means the core temperature of your body goes too high with severe health impacts. Now, that would be the case in optimal circumstances. The human body in good health, at rest, in the shade, without clothes. Generally, those are not the circumstances humans find themselves in. So the wet bulb temperatures can be significantly lower than that and still take a heavy toll on humans. Extreme heat can therefore be one of the deadliest events, with tens of thousands of casualties seen in the worst ones in recent times. For instance, the deadly 2003 European and 2010 Russian heat waves. We saw significant casualties from wet bulb temperatures no greater than 28 degrees C. Incidences where that happens are thankfully few and far between, as things currently stand. One key question is how much more frequent would they become with the various scenarios of how climate change might progress. A recent study showed a number of global instances where wet bulb temperatures went above 31 and 33 degrees C, and two stations that have reported multiple maximum values above 35. Now, these usually only applied for short periods, 1 or 2 hours, but they're an indicator of how close we are to these things happening more seriously. Computer modelling of the extreme, what's called the RCP 8.5 scenario, sometimes described as business as usual, but it's not, it's significantly worse than what we would actually expect to experience, suggests that wet bulb temperatures would regularly exceed 35 degrees C in parts of South Asia and the Middle East sometime in the third quarter of this century. But we already know that the modelling struggles with the behaviour of water vapour. So what we really need to know is what's actually currently happening. What are the trends? What do they tell us? The problem is that measuring temperature is one thing. It's relatively easy to do. Although even there, the fact that historically measurement was more focused on weather forecasting rather than long-term climate monitoring, that gave us all sorts of problems with the comparability of measurements over time. But the measurement of humidity is more problematic, and as a result we've only recently been able to put together even a vaguely passable first draft of data, which we now have, and I'll come to that in a moment. You need good data both over land and over sea. On land, stations now commonly measure either the wet bulb temperature, the dew point temperature, or relative humidity. Other aspects of humidity can then be worked out from those specific parameters. There's a wide range of instruments that measure each of those, and they all work in a slightly different way with different potential biases or types of error. Wet bulb thermometers, for instance, can be affected by ventilation extremes depending on their location. A reservoir important to its functioning may dry out or may freeze in certain situations, and so on. Lots of things that have to be monitored for and recorded and checked. For ocean measurement, it can be very important how high up the measurement is taken, because there's significant variation at relatively short elevations. Historically, most of the measurements were taken on ships. Interestingly, in recent years, temperature measurements are being taken more and more by floating buoys. But while they may be okay for measuring surface temperatures, they're closer to the water than the ships, and that can produce a degree of error when it comes to humidity. So really, you only want to use the ships for measurement of humidity. It shouldn't therefore be a surprise that we haven't had any kind of robust, reliable record of how humidity has changed over the last century. We do know what we'd expect to happen. As temperatures increase with global warming, we would expect more water vapour to be added to the air, and with those warmer temperatures, the air has a higher saturation point, so it can hold even more water vapour. It's been calculated that the air can hold around 7% more moisture for every degree Celsius of temperature rise. This is why we would expect heavier rainfall events, amongst a number of other things, in a warmer world. Now we've started to get to the point where we can actually get the figures for how this is playing out. The UK's Met Office has collaborated with a number of other agencies to put together the first iteration of a dataset that makes the most sense out of the historical measurements that we have and establishes the standard for measurements going forwards. It gives monthly average figures spanning from January 1973 to present on a global grid. The data coverage is not perfect. Global coverage is reasonable from the 1970s onwards, but not so good in the southern hemisphere as in the northern, not good at all at the poles. And there's no guarantee that even though it's seen as an important thing to measure, it's going to carry on being able to be measured effectively. The observing ships, I guess because of the use of buoys for surface temperatures, have declined from a peak of 7,700 in the 1980s to just 4,000 today. So that could become a real problem in the future. But in spite of all of that, we do have some figures. What do they tell us? They tell us that we have something of a paradox. As we would expect, specific humidity, remember that's the quantity of water vapour in the air, that has been going up as temperatures have risen. What you would find more surprising is that relative humidity, the percentage compared to the saturation point, that has been declining. And that's because although the land surfaces have been warming faster than the oceans, it's only the oceans that are the sources for most of the water vapour that enters the air. It's moved over the land by circulation. If we had a 100% ocean-covered planet, then in that situation you would expect to see exactly 7% increased water vapour for 1 degree centigrade of rise, an increase in specific humidity with a static relative humidity. Obviously that's not the world we live in. So here's the graph of relative humidity showing overall decline over the last 50 years. And you'll note that it includes both figures for land and ocean, and both have been overall declining. And that is the surprising aspect. You'd expect to see it declining for land. But the fact that it's declined overall as well for many regions of the ocean, it's not what you would expect to see. This is what Dr. Kate Willett, the lead author of the paper on this, had to say. This decrease is difficult to explain given our current physical understanding of humidity and evaporation. For example, the expectation from climate models is that ocean relative humidity should remain fairly constant or increase slightly. However, we also know that there are data quality issues with observations of relative humidity over the oceans, so the uncertainty around this declining trend is large. Hence the need for more and better analysis. People tend to think we measure all the important stuff already, but there is still a huge amount we don't know. Now, relative humidity isn't declining everywhere. So, for instance, one of the areas where we've seen historical instances of heat stress would be India, and relative humidity seems to be increasing there. This can be affected by human activities. So again, in India, the water added during irrigation of crops can increase the heat stress effects, even though it actually reduces the temperature slightly locally. Deforestation, urbanization, intensive agriculture, all of those can affect local moisture levels in one direction or another. You can't just look at the global averages and work out what that means for when and where you're going to get extreme heat stress events. So there's some of the detail. What does all this mean? The changes in humidity are complex, difficult to measure, not particularly intuitive for people to understand. So it's no surprise that nobody much talks about them. They do, however, make a huge difference to what's going to happen in the world, what's happening right now in the world. Increasing water vapour means that more will make its way into the atmosphere and add to the greenhouse gases, so amplifying global warming. There will be more rainfall, especially in heavy rainfall events. Hurricanes are likely to have more water to unload, adding to the damage that they cause. There'll be an increased risk of more widespread and longer duration heat stress events, with the potential loss of human life that they bring. The decrease in relative humidity may lead to more dry conditions in some places where wildfires can start more easily and spread faster, but a lot of the detail of this remains unknown. Here's Dr. Willett again. The decrease in relative humidity over land is really interesting. We do not see the same decrease in historical reconstructions from climate models, although we do see increasing temperature and specific humidity. This means that future impacts related to saturation and water vapour levels are a bit more uncertain, especially over those regions showing strong changes in relative humidity. The headline writers aren't going to focus on any of this, which is probably a blessing, to be fair, as much as anything, given their tendency to simply amplify worst case scenarios all the time. But for those of us that are really interested in what's going on in the world and aren't trying to impose presuppositions and agenda onto whatever data comes their way, as some people seem to be, these are important things that would be well worth watching out for as we fill in more of the gaps over the coming years. So this isn't one of those areas that lends itself to clickbait. I'm sure this is not going to be one of those viral videos, but I hope that nevertheless you found it interesting and found it useful. Let me know what you think in the comments below.